Hey everybody, I wanted to talk to you a little bit about reactions of alkenes. So let's go ahead and jump in. Okay, so chapter 8 is all about reactions of alkenes. Here are our learning objectives. Now we're going to go through quite a few reactions. I'm going to try to organize these into different ways that you can understand them. So kind of try to keep them organized in your brain. One good way of learning reactions of alkenes are just to make flashcards. A lot of students just make flashcards. But another way that you can make flashcards is to take some note cards and draw an arrow and write a reagent over the arrow. Or you can write a reagent and an alkene and hold up the alkene to yourself, hold up the reagent, and try to predict the product from that. That was one thing that was helpful for me as a student because we have certain classes of alkene reactions, and you can predict the products, and that is basically the type of problems that we're going to be dealing with. Is okay, if I take an alkene and I add this reagent to it, what's going to happen? What am I going to get from this? Now, another type of problem that we've talked a little bit about in the past is a retrosynthesis problem. And a retrosynthesis problem is where we actually have the product and we know the product, but we're trying to figure out how we got the product or the best way to make the product. And this is more of a real life situation where your boss comes to you and says, look, I need to be able to make this product. I need to be able to make it safely, cheaply, or I need to be able to get the most yield. I need it in the most pure way that I can get it. And I need you to figure this out for me. And so that's another type of problem. We call that a retrosynthesis problem because it's a working backwards problem. Retro meaning backwards, and synthesis meaning making. We're kind of making backwards, right? We're working backwards in our working out the problem. We're starting with the product and we're trying to work backwards and trying to figure out how to make that product from the product, not necessarily from the reactants like we would normally do with a predict the product situation. Okay, so our learning objectives for chapter 8, we're going to use the extended version of Markovnikov's rule. We're going to talk about Markovnikov's rule. We've talked about Zaitsev's rule. We've talked about our Kahn-Ingold prelog rules. We've talked about lots of different rules in organic chemistry. Organic chemistry has lots of different rules. We're going to add to that with Markovnikov's rule. Markovnikov's rule is one of the most famous rules in organic chemistry, and it's pretty easy to remember. It's not too hard. So we're going to use the extended version of Markovnikov's rule to predict the regiochemistry, which is the orientation of electrophilic additions to alkenes, okay? We're going to show how we can control the stereochemistry and regiochemistry of addition reactions to obtain the products that we want, and then show how to control the hydration of alkenes to give alcohols with either Markovnikov or anti-Markovnikov orientation, depending on the reagents. We have one reagent that gives us a Markovnikov product and one reagent that gives us an anti-Markovnikov product. Sometimes we say a Mark product or an anti-Mark product. We can predict the products of halogenations, oxidations, reductions, cleavage of alkenes, and include the orientations and stereochemistry of these reactions. Predict the stereochemistry observed in hydroboration reactions, halogenations, dihydroxylation reactions of alkenes. You can see we're really diving deep into the reactions of alkenes. We're going to learn all of these different reactions. Now, we're going to learn these reactions not on a mechanistic level. So we learned SN1 and SN2, E1 and E2 reactions very deeply, and we are going to learn electrophilic addition reactions deeply. And we do have a bunch of different kind of flavors of electrophilic addition reactions. Electrophilic addition reactions are the reactions that alkenes tend to undergo, but we're not gonna learn these reactions to the depth that we learned SN1 and SN2 reactions. We're going to learn them in a predict the product depth. Okay, so we're going to learn very wide but not very deep with these reactions. We need to learn a lot of different reactions and be able to predict the products of these reactions. You could propose logical mechanisms to explain the observed products of alkenes and include regiochemistry and stereochemistry. Just be able to think through possible mechanisms. You don't have to memorize those. And then use retrosynthesis to solve multi-step synthesis problems with alkenes as reagents, intermediates, or products. Okay, so we need to think through all of our substitution reactions that we've learned so far and all of our elimination reactions that we've learned so far. And we're going to add in all of these reactions of alkenes into our reaction toolbox that we have. We're going to use clues provided by the product of reactions to determine the structure of an unknown alkene, and also show how metathesis interchanges the alkadine groups in alkenes, which form new and different alkenes. And then we're also going to talk very briefly about polymers. Polymers are a fairly new when we talk about organic chemistry. Organic chemistry reaches centuries and centuries into the past, but polymer chemistry is a rarely recent development in organic chemistry, and we're going to talk briefly about polymer chemistry toward the end of the chapter. Okay, so what we need to talk about is carbon-carbon double bonds. Of course, we want to start with carbon-carbon double bonds because we're talking about alkenes. Alkenes have a carbon-carbon double bond. And when we think of double bonds, we need to think about electrons, okay? Remember that double bonds are electrons. All bonds are electrons. And sometimes when we look at these lines, we forget that those lines are made of dots, right? Those lines, when we were beginning to draw Lewis structures, we drew all those little dots around those little atoms, and then those dots came together to form lines. But what we really need to remember is those lines are made up of electrons. Those bonds are made up of electrons, and the density between these two carbons and the electron density makes this carbon-carbon double bond actually very nucleophilic, and we're going to talk about that in a little bit, okay? Now, the most common reactions of double bonds eliminate the double bond, okay? Now, remember that a double bond is made up of a sigma bond and a pi bond, and that second bond in the double bond is a pi bond. And the most common reaction of double bonds transform that pi bond into another sigma bond, okay? So that we have all single bonds. Those are the most common reactions of double bonds. Okay, so here are some different types of alkene reactions. We have addition reactions. Now you will notice that two of these, when we look at them, so let me just go on and talk to you about the slide before I try to make big, broad statements, okay? So an addition reaction, we are adding something across the double bond. And this is what we are really going to spend the most of our time on in this chapter. In fact, with alkenes, electrophilic addition is one of the main types of reactions that alkenes undergo. So if we have an electrophile, okay, so this is something that is looking for electrons. Our double bond acts as a nucleophile, okay, and can actually reach out. And what ends up happening is we add both of these across the double bond, and we end up with all sigma bonds, okay? Now remember that alkenes are typically made through elimination reactions. Those elimination reactions usually follow Zaitsev's rule. Don't forget, we have E1 and E2 elimination reactions, and we talked a lot about those in the last chapter. So go back and review that if you need to, okay? And then alkenes, we can talk about substitution reactions, but we're not going to spend too much time on that, okay? We really want to focus in on addition reactions this chapter. So bonding in alkenes. So electrons in the pi bond are loosely held. Remember that they are above and below the internuclear axis. So carbon-carbon atoms are here. These represent the nuclei of these carbon atoms. So we have an internuclear axis here, and our sigma bond is right there in between the internuclear axis. But our pi bond, okay, so don't forget, just a little review here, that these three, so here, here, and here, these three sigma bonds, okay, we're going to assume that these are hydrogens, okay? These three sigma bonds are created through sp3 hybridization, okay? And they are they're all in one plane. This pi bond here is created through an unhybridized p orbital that is sticking up perpendicular to that plane at 90 degrees and is above and below the internuclear axis. Now, what this does is it causes these electrons to be kind of loosey-goosey out there in space, okay? So it can actually act like a nucleophile. It is not an unshared pair of electrons. You're going, oh, okay, Ms. Carter, wait, you're changing the game on me, okay? You're saying that now all of a sudden a nucleophile does not have to have an unshared pair of electrons, because clearly a double bond is not an unshared pair of electrons. You're right, okay? A nucleophile, we have said so far, has to have an unshared pair of electrons. At this point, though, we are also going to define a nucleophile. We're also going to say that a pi bond can also, a nucleophile can also have a pi bond, okay? Because what happens is this pi bond acts exactly the same as an unshared pair of electrons. It hangs out there in space, okay, outside of the internuclear axis, okay, and can actually attack an electrophile just like any other nucleophile can, okay? Okay, these reactions are called electrophilic addition reactions. Okay, so let's talk about the steps of electrophilic addition. So the pi electrons, okay, we're going to define these pi electrons as part of our nucleophile now. So anything that has a double bond can act, especially carbon-carbon double bond, can act as a nucleophile. Those pi electrons are going to attack the electrophile, okay? This creates a carbocation intermediate. Remember that carbocation intermediates always want to be on the most substituted carbon, because tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations, okay? So our carbocation always wants to be on the more substituted, okay? And then the nucleophile comes in and attacks, okay, so what is left comes in and attacks the carbocation. And we're going to talk about where this nucleophile comes in just a second, okay? Okay. So here are all of the different types of our electrophilic addition reactions, okay? So we have a hydration reaction is a type of electrophilic addition. Hydrogenation, okay, so hydration is where we're adding, so here above the arrow is the type of reaction, below the arrow is what we're actually adding across the double bond, okay? So a hydration reaction adds water across the double bond. So we're gonna add a hydrogen to one carbon and an OH to the other carbon. Hydrogenation reaction adds two hydrogens across the double bond, okay? A dihydroxylation adds 2 hydroxyl groups, okay? Oxidative cleavage, okay, is a little bit more complicated. Oops. But we're adding oxygen, okay, across the double bond. Epoxidation actually adds 1 oxygen across the double bond, and it adds it to the same carbon, which creates a small 3-membered ring, okay? Halogenation adds a double halogen, okay? We could also, remember, call this a vicinal dihalide, okay? So Br2. A halohydrin, remember, a halohydrin is a halogen and an OH group on adjacent carbons. Okay, we're adding across the double bond. And then we can kind of keep going on from there. Okay, so there are a whole bunch of different types of electrophilic additions. Okay, so our mechanism of electrophilic addition of a hydrohalogen, okay? So like hydrobromic acid. So our double bond is going to attack our electrophile. Our hydrogen is our electrophile. Our bromine, okay, takes both of the electrons with it, okay? And we end up with a carbocation on our most substituted carbon, which these carbons are actually symmetrical, so it really doesn't make a difference, okay? And we end up with a bromine ion, which then also becomes a nucleophile. That nucleophile then attacks the carbocation. Okay, so we have a 2-step mechanism. Now, Markovnikov's rule. So Markovnikov's rule says that the addition of a proton, okay, which is a hydrogen, to the double bond of an alkene results in the product that has an acidic proton bonded to the carbon atom that already holds the greater number of hydrogens, okay? In other words, let me go back and show you. If this carbon had a carbon here, okay, and this was carbon, carbon, our carbocation would form on this carbon, and the carbon that already had the most number of hydrogens would gain the hydrogen, okay? I have always taught that the easiest way to remember Markovnikov's rule, okay, is that the hydrogen goes with its friends. The hydrogen always goes to the carbon that has the most number of hydrogens on it, okay? And the reason is, in the extended Markovnikov's rule, what your book wants you to know is that it generates the most stable carbocation intermediate. The reason that the hydrogen goes with its friend is because the carbocation will form on the carbon that has the most carbons attached to it already, because a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, okay? So the extended Markovnikov's rule is based on carbocation stability, in that our most substituted carbocation is the most stable, okay? And so the hydrogen goes where the carbocation is not, which is usually with where the most hydrogens are, okay? So if you can remember that the hydrogen goes with its friend, you can remember Markovnikov's rule. Okay, so let's look at this example. This is actually the same example, kind of the same example that we just looked at, where I told you if there was a carbon attached to it, this is what would happen. So let's look at this, and we have 2 different scenarios, and one is what's going to happen and one is what's not going to happen, okay? So here, let's look at our substrate first, okay? We have a carbon here that has 2 carbons attached to it, and then we have a carbon here that has a hydrogen and a carbon. Okay, so this carbon doesn't have any hydrogens attached to it. This carbon has a hydrogen attached to it. But if we use Markovnikov's extended rule and we think, why is this going to happen? Our carbocation is going to form on this carbon because it is the most substituted carbon. At that point, it will be a tertiary carbocation. It will have 1, 2, 3 carbons attached to it, whereas this carbon will only have 2, 1, 2, and then it will have a hydrogen, okay? So the hydrogen is going to go on this side of the double bond, okay? The carbocation will end up on this side of the double bond, and then also the bromine will end up on this side of the double bond. Okay, so what this is showing you is that we will not get a carbocation here. Okay, we will get the carbocation, we will get a tertiary carbocation, not a secondary carbocation. Okay, so according to Markovnikov's rule, we're going to produce the most stable carbocation that we can. And the implications of this are that the hydrogen will always go with its friend. Okay, so then the bromine adds to the most substituted carbon, which is the one that the carbocation is formed on. Okay, so let's look at this example. Here we have a hydrogen and we have a carbon. When the nucleophilic double bond attacks the hydrogen's going to go with his friend, okay? We're going to form the carbocation on the most substituted carbon, which is going to be this side of the double bond, and the bromine's going to attach here. This is not going to happen, okay? Now remember, we're going to add the hydrogen on one side and the bromine on the other, okay? So we're going to do that. We're always going to have the hydrogen on one side and the bromine on the other. The hydrogen is always going to add to the side that already has hydrogens on it. If both sides are symmetrical, then we're going to get a 50-50 mixture, okay? Because it won't really know where to add. Okay. Oh, the solution is here. Okay, well, I didn't animate it properly. Convert 1 methyl cyclohexene to 1 bromo, 1 methyl cyclohexene. Okay, so I don't know how to cover this up. I can't, but let's just look at it. Here's the answer. Okay, so the synthesis requires the addition of hydrobromide to an alkene with Markovnikov orientation. Okay, so here we have 1 methyl cyclohexene. If we add HBr to it, we can anticipate that the hydrogen is going to go on this side and the bromine will add to the most substituted carbon. Okay. I think I said methyl cyclohexene. It should be methyl cyclohexane. Okay, so here's some more examples. Okay, you can pause the video, look through them a little bit, but these are exactly like the ones we've already looked at. Wherever the double bond is, okay, we're going to add the halogen to one side and the hydrogen to the other. The hydrogen is going to go onto the carbon that has the most hydrogens already on it, and the halogen is going to go onto the most substituted carbon. Okay, now, in the presence of peroxides, okay, we can add HBr to an alkene and form an anti-Markovnikov product, okay? Now, peroxides produce free radicals, and only, I'm gonna start yawning again, y'all. Only hydrobromic acid has the right reactivity for each step of the free radical chain reaction to take place, okay? We call this the peroxide effect. It only happens with hydrobromic acid. We don't see this with hydrochloric acid or hydroiodic acid because the reaction of an alkyl radical with HCl or HI is strongly endothermic, okay? So we can only do this with HBr, okay? Okay. Here, this is in your book. I'm not going to spend too much time on it, okay? But this is a multi-step synthesis, and you need to think through these, okay, as you are learning. I think it is. Let me read it. Hold on. Convert 1-methyl cyclohexanol to 1-bromo 2-methyl cyclohexane. Okay, sure. Yeah, so this is a multi-step synthesis. So we are given an alcohol, okay, and we're trying to convert it to an alkyl halide, okay? We don't know how to do that directly, but we do know how through elimination to convert an alcohol to an alkene, okay? And then once we convert our alcohol to an alkene, we do know how to achieve an anti-Markovnikov product by adding hydrobromic acid and peroxide. We write peroxide ROOR, okay, because this OO is the peroxide, okay? And so this gives us an anti-Markovnikov product, which would add the BR in the anti-Markovnikov spot right there, okay? The hydrogen doesn't go with its friend here, okay? The hydrogen goes on the other side. The hydrogen goes with the carbons here, okay? So look over this example and make sure that you understand it. But this is what's called a multi-step synthesis reaction, and we're going to get more problems like this where you may not have the it may not be a one-step synthesis reaction, but you may have to figure out how to synthesize your raw materials in order to synthesize your product. So here's the summary of our two-step synthesis. Okay, now hydration of alkenes. This is the first reaction, the first electrophilic addition reaction that we're really going to look in close at, talk about reagents of, predict the products of, okay? Hydration of alkenes, we're adding water across the double bond. So we're adding 2 hydrogens. I do know what water is. 2 hydrogens and 1 oxygen. And we're adding that across the double bond. So we'll add 1 hydrogen on 1 carbon and then an OH on the other carbon. And we have 3 different ways that we're going to do this. The first one is called acid catalyzed hydration. And then the second is oxymercuration, demercuration. And then the third way is called hydroboration, oxidation, okay? And there's reasons that we want to use, we would want to use each of these different reactions. Okay, so hydration, let's talk a little bit about hydration of alkenes. If we use acid catalyzed hydration, we will get a Markovnikov product, okay, Markovnikov orientation. But hydration of alkenes is just addition of water across the double bond. It gives us an alcohol because we're adding a hydrogen on 1 carbon and then we're adding an OH to the other carbon, so our product is an alcohol. And the addition when we're using acid catalyzed hydration follows Markovnikov's rule. And then the reverse is dehydration, which we talked about when we talked about elimination reactions. Good reagents to use are dilute solutions of sulfuric acid or phosphoric acid, okay, H2SO4 or H3PO4. Okay, here's the mechanism. It's very similar to the mechanism of the electrophilic addition mechanism. We talked about that already, okay? And you do need to know the electrophilic addition mechanism. Now, remember that when we use acids, we end up with hydronium ion, okay, in water. So what happens is our nucleophilic double bond attacks our hydronium ion, okay? And so we end up with a carbocation intermediate and a neutral nucleophile, okay? Keep doing that. A neutral nucleophile. And then remember when we talked about SN1 reactions, okay? When we have a neutral nucleophile and it attacks the carbocation intermediate, then we end up with a positively charged product. So what has to happen is we have to have a third step. Anytime we end up with a positively charged product, which happens because we have a neutral nucleophile, we end up with deprotonation of our our product, okay? And that's going to happen to give us our neutral hydration product, our neutral electrophilic addition product. So we actually regenerate our acid here. That's why it's called acid catalyzed, okay? Remember, you guys, okay, this is really cool. Remember that a catalyst is always regenerated. It's not consumed in a reaction, okay? So we start with a H3O plus and we end with a H3O plus. Catalysts aren't consumed through chemical reactions. They're regenerated through chemical reactions. They're used, but they're recreated so that they can be used again. Okay, so orientation of hydration it follows Markovnikov's rule. Okay, the hydrogen goes with its friend. The positive charge always appears on the more our carbocation always appears on our more highly substituted carbon. Now, okay, here's the tricky part. Okay, we have possible rearrangements, but anytime. Okay, so this is something that you need to know. This is very important. And my past organic chemistry classes have really joked with me about that. I say this about everything. Okay, they're like, everything can't be really, really important, Miss Carter, but this is. Okay, I promise. This is really, really, really important. Anytime in a chemical reaction that you have a carbocation intermediate, you have the possibility for hydride shifts and methyl shifts. You have possible rearrangements, okay? So anytime, I'm going to say it again, anytime that you have a carbocation intermediate in the middle of a reaction mechanism, you have the possibility for a skeletal rearrangement, which is a hydride shift or a methyl shift, okay? Because that carbocation wants to try to get to as stable as it can possibly be, okay? It wants to try to be as stable as it can possibly be. So let's look at this example. Here we have a carbocation. Now, remember back, let's refresh just a second, okay? A positive charge can only travel one carbon over, okay? And it can exchange itself for a carbon or a hydrogen. It tries to exchange itself for a hydrogen, and if there's no hydrogens available, it's going to exchange itself for a carbon, which we call a methyl shift, okay? So let's look at this example here. Here we've generated a secondary carbocation. So what we're going to do to look out for methyl shifts is we're going to look to the right. Okay, that's a primary carbon. He's not any more stable. But then if we look to the left, holy smokes, there's a tertiary. That's actually, yeah, that's a tertiary carbon. Okay. It's actually, yeah, a quaternary carbon. But to move our charge over there, there's no hydrogens. So we have to move our carbon over here and our positive charge over there, and that makes our carbocation more stable. It becomes a tertiary carbocation as opposed to a secondary carbocation, and that's where that carbocation wants to be. He's going to kick that methyl group over so that he can be on the tertiary carbon because that's a better place for him. Okay, so let's talk about oxymercuration demercuration reaction. This is another way to do hydration, okay, but we don't go through a carbocation intermediate. So because of this, it's a better process than acid catalyzed hydration because we don't have the possibility for rearrangements. Still Markovnikov product, okay? So it's another way to do hydration without the possibility of rearrangements. We still have Markovnikov addition of water to the double bond. Overall, the reaction is the same exact net reaction, but we don't have the possibilities of hydride shifts or methyl shifts, okay? It's milder conditions than direct acid catalyzed hydrations, but here again, we don't have the possibilities of rearrangements or polymerizations. Which is a really good thing, okay? Okay, the steps. What happens first, okay, is we have mercuric acetate. It's this Hg, and then it's got two acetates here. So it looks like this, okay? And in the presence of water, what happens is we add a hydroxyl group to this carbon, and then we add that mercuric acetate to this carbon, and then we add sodium borate to the process, and it removes that mercuric acetate. And we end up with a Markovnikov product. Hydration. Our overall reaction is a hydration reaction with a Markovnikov orientation. You don't have to know the mechanism of this, okay? You don't have to know the mechanism. Okay, the rearrangement is mercury 2 acetate. It dissociates slightly to form an ion, okay? And it's an electrophile that adds to the pi bond, okay? So the Hg plus is the electrophile that adds to the pi bond. So the pi bond reaches out and attacks the that ion. The intermediate is a three-membered ring called a mercurium ion. And because of this mercurium ion, this is why the overall reaction follows Markovnikov's rule without the possibility, because we don't have the possibility of a carbocation rearrangement. So we follow Markovnikov's rule. So here's a picture where you can see where we form this three-membered ring. So this is why we don't have any, this mercurium ion here is why we don't have any rearrangements, any skeletal rearrangements. Okay. We call this an anti-addition because, and it's not important now, okay? When we get to alkynes, we'll talk more about it, but what happens is we form this little three-membered ring, this little mercurium ion. The water comes in and attacks from the bottom face, okay? And we call it an anti-addition. So water approaches from the opposite side of the ring. If we do have a ring, this does become important if we have cis-trans isomerism, because we end up with anti-addition. Okay. Now, that was the first step of our oxymercuration. Then we have what's called the demercuration step, okay? And we use sodium borohydride. I think I called it sodium borate a second ago, but sodium borohydride comes in and removes the mercuric acetate. Okay, when the sodium borohydride comes in and removes the mercuric acetate, that leaves us with our alcohol and our Markovnikov product. We still get our hydroxy group, our hydroxyl group on the most substituted carbon, and the hydrogen goes with his friends. Okay, goes on the carbon that has the most hydrogens. Okay, now we're going to talk about alkoxymercuration. Oh wait, this is the same thing. If the nucleophile is an alcohol instead of water, okay, so if we have an alcohol, if we have an R group attached to it instead of water, we end up with an ether, which is kind of cool. It's an ether synthesis reaction. So if our nucleophile is an alcohol instead of an ether, we plug that whole R group here. Okay, hydroboration oxidation. Okay, so hydroboration oxidation, H.C. Brown of Purdue University discovered that diborane, okay, which is B2H6, adds to alkene with an anti-Markovnikov orientation to form alkyl boranes, which after oxidation gives us anti-Markovnikov alcohols, okay? So this is a little bit similar to our, when we use our peroxides with our alkyl halide or with hydrobromic acid, except we can do this with hydration reactions, okay? But we have to use what's called hydroboration oxidation, okay? So what we're going to do, and he actually received the Nobel Prize in chemistry for his work in the field of borane chemistry. So what we do is we take borane, BH3, borane, and then this is in tetrahydrofuran, which is a common solvent. It's a aprotic solvent, polar aprotic solvent. And we can use this, okay? We can do a hydroboration reaction, and we add the hydrogen to one side, and it adds it creates an alkyl borane, okay? It adds a BH2 to the other side, and then when we do the oxidation reaction with peroxide, okay, like hydrogen peroxide, we end up with our OH group on the hydrogen side, okay? So in an anti-Markovnikov addition. So we can do this with diborane, okay? So here's how they create the BH3THF, okay? So here's the tetrahydrofuran complexed with the borane. So here, the borane adds to the double bond in a single step, with boron adding to the less substituted carbon and hydrogen adding to the more highly substituted carbon. So this is how we get the anti-Markovnikov product, okay? So here we have our double bond, okay? And this is our most substituted carbon. And our hydrogen adds to our most substituted carbon, and our borane, our boron from our borane, adds to our least substituted carbon, so that when we do our oxidation step, we end up with our hydrogen on our most substituted carbon, and then we cleave off of our borane and add our OH group, and we end up with an anti-Markovnikov hydroboration oxidation product. Okay, so oxidation of the alkyl borane with basic hydrogen peroxide produces the alcohol, and the orientation is anti-Markovnikov. Now, stoichiometry-wise, we can take 3 moles of an alkene. 3 moles of an alkene can react with each mole of borane. Okay, so 3 moles of alkene can react with each mole of borane. Now, the hydroboration step adds the hydrogen and boron to the same side of the double bond. We call this a syn addition. This is the opposite of the oxymercuration-demercuration reaction, which is an anti-addition, okay? So when the boron is oxidized, the OH keeps the same stereochemical orientation. So they end up, the OH and the hydrogen end up on the same side or the same face of the ring, okay? Now this ends up that it is trans because we have a methyl group, because we're talking about a hydrogen, okay? So hydrogen would make it a trans, okay? So be thinking about that. But it adds on the same face of the ring, which we call a syn addition, the hydrogen and the hydroxyl group. Okay, so those are our hydration reactions. Now let's talk about addition of halogens. Okay, rearrange a little. Okay, so chlorine, bromine, and sometimes iodine add across the double bond to form a vicinal dihalide, okay? Remember, vicinal just means that it's on adjacent carbons. Geminal means that it's on the same carbon. Vicinal means that it's on the adjacent carbons. This is called an anti-addition. Now here it doesn't make a big difference because we have rotation around the single bond, but if we had a ring, it would make a difference because those would be locked in place. Okay, here's an example. Okay, so the stereochemistry results from the backside attack of the nucleophile on what's called a bromonium ion. And a bromonium ion forms a small little three-membered ring on one side of the face. So because it's on one side of the face, the other bromine has to come in to the opposite side of the face, which results in an anti-addition. So one bromine is added to one face of the ring and the other bromine is added to the other face of the ring. And this usually results in a trans product. Okay. Now, we can also form halohydrins, okay? So if a halogen is added in the presence of water as a solvent, we will form what's called a halohydrin. And a halohydrin is where we add a halogen on one side of the double bond and a hydroxyl group on the other side of the double bond because water is our nucleophile, okay? Now, this is Markovnikov addition because the bromide or the halogen will add to the less substituted carbon. So in other words, the halogen is our hydrogen, okay? Because the water is our nucleophile. This also adds with anti-stereochemistry. So we add the OH group to one face of the ring and the halogen to the other face of the ring. We form these small halonium ions, okay? If it's a chlorine, it's a chloronium ion or a bromonium ion, okay? And that forms, it bears more positive charge than the less substituted carbon, okay? And so then attack by water occurs on the more substituted carbon to give our Markovnikov product. So the halogen will go with the hydrogens. Okay, so not only does the hydrogen go with its friends, halogens and hydrogens stick together when we're talking about halohydrins. Okay, now let's talk about catalytic hydrogenation. So I believe we have talked about catalytic hydrogenation in the past, but catalytic hydrogenation is just adding hydrogen across double bonds. And we usually do this with a precious metal catalyst. Okay, so we have a double bond. We add hydrogen, and this hydrogen is typically it is gas that is flowing over the surface of some sort of solid precious metal, such as platinum, palladium, or nickel. Okay, and it's a catalyst, so it's not consumed. It can be used over and over and over again. The catalyst is, but we call it heterolytic. I just lost the word that I was going to say. I can't remember what I was going to say. So it's in different phases, and there's a word for that, and I'll let you guys know what the word is. But it's catalytic hydrogenation. So typically our alkene is in the liquid phase. Our hydrogen gas is in the gas phase, and then our catalyst is in the solid phase. So we have many different phases going on. And so we add our hydrogen across the double bond. Now this only happens if we have a catalyst that is there. Okay, now we can determine where the hydrogens add. You know, you may be thinking, hydrogens are just hydrogens. Why do we care, right? But we can decide, we can figure out exactly which hydrogens and how they're added, okay, by having something that already has deuterium on it, okay? So here we have cyclohexene, okay? And it has two deuteriums attached to it. Deuteriums are hydrogens that have a neutron in the center of them. They have it's called a heavy hydrogen. And then we flow hydrogen over our precious metal catalyst, and we find that we have a syn addition, okay? So the hydrogens are both added to the same side of the ring, okay? So the hydrogens insert across the same face of the double bond, and the reduced product is released from the metal. So what's actually happening is we have our metal, precious metal catalyst, the ring is coming in and touching and grabbing both hydrogens on the same face before it leaves, okay? And so we would say that this is syn stereochemistry, because they are on the same side of the double bond. Heterogeneous catalyst is what I was thinking of earlier. I don't know why my brain just kind of just had a brain lapse. Okay, so Wilkinson's catalyst is a soluble homogeneous catalyst. So in other words, it can go into the liquid phase. We don't have to have a slab of it in order to flow hydrogen gas over and our liquid alkene. We don't have to have three different phases of stuff going on, okay? So Wilkinson's catalyst is a soluble homogeneous catalyst that catalyzes the hydrogenation of a carbon-carbon double bond, okay? And Wilkinson's catalyst has rhodium in the center. And then we have this phosphorus and 3 phenyl groups, okay? It looks like this big giant thing. Okay, you don't have to know the structure of it. You don't be able to draw the structure of it. Heterogeneous catalyst. Okay, so here's a good picture of the syn stereochemistry in catalytic hydrogenation and exactly how it works. So we have a solid heterogeneous catalyst, and it adds 2 hydrogen atoms on the same face of the pi bond, okay? So here we have our pi bond, okay? We have our double bond. So here's our pi bond. This is our original sigma bond. Nothing changes with it. Here's our ring. Here's our deuterium that are just there for kind of landmarks to make sure we don't confuse which are the old hydrogens and which are the new hydrogens, okay? So we have those guys there kind of saying these are our old hydrogens. And we want to figure out which ones are the new hydrogens. So what happens is we dope up our catalyst, and it absorbs a lot of hydrogen. So the hydrogen is on the surface of our precious metal catalyst, and here's our catalyst with the hydrogen absorbed. So this is a big slab of platinum, okay, not the cheapest stuff in the world. Oops. Okay. So here it is, and our ring comes down and sits down on our catalyst and grabs the hydrogens both on the same side, okay? And then it releases, the alkane product is released. But you can see how there's an actual physical system here where the ring actually comes and sits down and grabs those hydrogens and then is released from the product, because it's one big slab. It's actual surface that it's got to grab them from. Okay, so a solid heterogeneous catalyst adds 2 hydrogen atoms to the same face of the pi bond. We can't really flip them like pancakes, you know. They have to come in and sit down on one side, so both hydrogens are added to the same side of the pancake. Okay, let's talk about carbines, okay? Carbines are particularly useful. So a carbine is a CH2 group, okay? And it's not an ion or a radical, but it's a pretty unique thing. So it's a CH2 group that has an unshared pair of electrons, okay? Um, we can take a carbene, okay, um, and react it with an alkene to create a cyclopropane ring. And we have three methods of doing this. Okay, cyclopropane rings are particularly valuable. They're high energy products. We can do this through diazomethane. We could do this using a Simmons-Smith reaction. We can do this using alpha elimination of a haloform. So let's talk about exactly what these are. Okay, so these are ways we can create carbenes, okay? So the diazomethane method, okay? We take diazomethane, okay, and through heat or UV light, we create nitrogen gas and our carbene. Okay, we got some problems here. Okay, diazomethane is extremely toxic and explosive. I particularly don't want to volunteer for this process. I don't know about you. Okay, I don't. So the carbene can insert into carbon hydrogen bonds too. This isn't a great method. Let's move on. Okay, Simmons-Smith reaction is the best way, okay, for preparing cyclopropanes, okay? We don't have to go through a carbene. We can create our cyclopropanes by using an alkyl halide, zinc, and copper chloride, okay? Copper 1 chloride. When we do this, we create what's called the Simmons-Smith reagent, okay? It's also called a carbenoid. It is carbene-like, but it's not a carbene, okay? So what we do is we write this over the arrow so that we know that where the double bond is, we create a small little cyclopropane ring. Pretty efficient reaction. Okay. And then there is an alpha elimination reaction, okay? Alpha elimination reaction, we can use chloroform or bromoform, okay, to be dehydrohalogenated to form a carbene, okay? Then, of course, with that carbene, we can react it with an alkene, okay, to give our cyclopropane. Okay, so here's like potassium hydroxide. We can take bromoform, potassium hydroxide, keep going with the reaction, and we can get dibromocarbene. Now, this dibromocarbene, let's see, I think we're going to talk about it. Yes, okay. Okay, this gives us dibromocarbene. It gives us a carbene. Now, that carbene has the dibromocarbene has a bromine here and a bromine here. Okay. So cyclopropanes retain the cis or trans stereochemistry of the alkene. Okay, so if we have an alkene that is trans, okay, then our cyclopropane will also be trans in stereochemistry. Okay, here's an example where we have our alkene that is cis in stereochemistry, and when we do our alpha elimination reaction, we also get a cyclopropane that is cis in stereochemistry. Now notice that we end up with geminal dihalides, okay, on our carbon. Okay, so here's Here are the overall reactions. Here's the Simmons-Smith reaction to generate our small little cyclopropane. Remember, this is the best one, okay? Our alpha elimination reaction, we end up with geminal dihalides. Okay, now let's talk about epoxidation. This is another reaction that we can use stop there. He's too strong of an oxidizing agent. Okay, so what he actually does is he actually cuts the double bond in half and adds oxygen. Okay, and adds oxygen. Okay, and here, let's say we have a methyl group. Okay, this is going to stay this way. But here we have a hydrogen. He's even going to keep going. He's going to take this hydrogen and turn it into an alcohol because he's not happy with having just hydrogens. Okay, so everything is going to get as oxidized as it possibly can get. So if we end up with an aldehyde, that aldehyde is going to get completely oxidized until it's a carboxylic acid. And a carboxylic acid is a carbonyl carbon. Three methods of polymerization: cationic polymerization, free radical polymerization, and anionic polymerization. So the cationic polymerization uses a carbocation intermediate, and the anionic polymerization uses a carbanion intermediate. Carbanions on the whole are very rare. We do talk about them briefly. We will talk about them briefly. But we don't see them very often, not nearly as often as we see carbocations. So cationic and free radical polymerization are our most common types of polymerization. Okay, so let's talk about cationic polymerization. It's typically catalyzed through its acid catalyzed polymerization. So we come in and we have an acid, sulfuric acid, phosphoric acid, that comes in and creates our carbocation intermediate by um, uh, through electrophilic addition, basically. We create a carbocation intermediate. Okay, that's why we're talking about it right now, is our pi bond from our double bond. Okay, and then what happens is we have our pi bond from our double bond attacks that carbocation, which produces a dimer. Okay, and then our next alkene reacts with that carbocation, okay, which forms a trimer, and so on and so on and so on until we form long chains of this polymer. Okay, now eventually we have to get to a termination step. And just like our radicals, we have propagation, elongation, termination. Okay, so the chain growth ends when a proton is abstracted by the weak base of the acid that is used to initiate the reaction. Okay, so this weak base is titrated to figure out how much is needed to create how much polymer you need. Okay, so the chain growth, the loss of the hydrogen forms an alkene and it ends the chain growth. Okay, so the very last monomer will actually be an alkene, and that's the termination step. Boron trifluoride can also be used as a catalyst, okay, such as in polystyrene, okay, like styrofoam. So we have our first propagation step where we have water that attacks the boron trifluoride, creating this complex. And then styrene, it's the same process where we have our nucleophilic double bond attacking our electrophilic cation. Okay. So here we go. Here's what we end up with. We'll have our first chain lengthening step, and then it continues. Okay. And then termination of the polymer chain. Again, our last monomer unit will have a double bond. Radical polymerization, what typically happens is we have a radical. You have to have an initiator, such as peroxide, and that radical, so one of the electrons from the pi bond in the double bond will go toward the covalent bond formed by the radical. The other will go on to the other carbon, and then the next two guys will form a covalent bond together using one of each, and you'll have a growing chain. Okay, and then anionic polymerization, don't focus too much on this, but we have a little bit of a base, okay? Superglue functions this way. We have a little bit of a base, and then we have our chain lengthening step where we keep creating our highly stabilized anion over and over and over again, our growing chain, okay? Oops. And our elongated chain, and this ends up with, now we write polymers, one way that we write polymers, it's polymer notation. We put our monomer in big brackets, okay? So here would be 1 unit of our monomer, and then we write N, okay? And that means we repeat this monomer over and over and over again, and then we can write our very last monomer here and our end monomers here, and then these are our central monomers, and they're repeated over and over again. Okay, sometimes millions of times, many, many times. Okay, and let's talk about metathesis. Okay, we can think of a double bond as two alkylidine groups. alkylating groups. I can't talk today. I'm sorry. So let me explain what I mean by this. When we have a double bond here, okay, we can divide our double bond into two groups down the center, okay, where one side, alkylidine groups, there we go, alkylidine groups. One side of our double bond is one group and one side of our double bond is the other group. And then we have one side of this double bond is one group and one side of this double bond is another group. Remember back from general chemistry, we talked briefly about metathesis reactions. Metathesis reactions is like trading partners at a square dance, okay? That's all that metathesis means. It means to trade partners, okay? And that's exactly what can happen in an olefin metathesis reaction. So olefin is an alkene, and an olefin metathesis reaction is where we use a catalyst, okay? And we end up with one side of our double bond connected to another side of a partner's double bond, okay? So here we have a cis A, okay? We use a catalyst and we end up with a cis plus trans, okay? So olefin metathesis is any reaction that changes and interchanges alkylidine groups. Okay, so that's olefin metathesis, and that's all we're really going to talk about as far as that goes. Okay, chapter 8 homework is going to take you a little bit more time than the other homeworks. Okay, this is a bigger chapter. We deal a little bit more with reactions. It's a little bit more to digest. I would like for you to spend more time on it. I'm going to give you until Monday night. It says Sunday night. I'm going to give you guys until Monday. Actually, it's fall break. I don't want you guys to get behind, though. I'll give you guys till Tuesday night at midnight, okay? I don't want you to spend your fall break doing it. I'll give you guys till Tuesday night at midnight, but don't wait till the last minute, okay? I'll give you guys till Tuesday night at midnight to get your Chapter 8 homework and your alkene reaction names and outcomes done. It's going to take you a little bit longer on your Chapter 8 homework, but so don't wait. Allocate some extra time. Make flashcards, okay? Whatever you need to do to memorize these reactions. Something else I was going to tell you. It'll pay off when we get to reactions of alkynes, because reactions of alkynes are not too different from reactions of alkenes, okay? So good luck. Message me if you have any questions or any trouble. Let me see if I can get out of here. Okay, good luck. I'll see you guys later.